Hey everyone. Well, it's been a bit of a time since my last update. Quite a bit of time actually. And the main reason for that is, once again, I got busy with work. I got busy with some other projects that are coming up. And honestly, a lot of the work that I had done leading up to this was kind of just disassembling. It was stuff I could do on my own, stuff I could just really quickly, run through, take video of, popping bolts and nuts out and taking the parts off the engine really wasn't that big of a deal. It's not that difficult to do. So that's kind of why my videos have been progressing as fast as they have up until this point. So I had a bunch of videos shot, just sitting on the camera here, about measuring the crankshaft journals, measuring the camshaft journals, those kind of things. Just start measuring some tolerances, figuring out how to measure the bores in the engine. And I was gonna kind of post that together as one film. And unfortunately, I needed a set of micrometers for measuring the mains because they're a certain size and I have to set my bore gauge to that. And unfortunately, those took so long to come in that I had to cancel the order and ended up ordering another set that said they would ship within a few days. Ended up shipping from India, and it took 2 weeks to get here. So finally have those calipers in, and I'm kind of a perfectionist. I don't want to just throw something out there and then have to update it later. So I sat on the video and I've just been waiting. It's not for lack of trying though, as far as getting other stuff done. There's actually the engine torn down. I had a friend of mine come in from out of town to help me do some of the work on the head. He wanted to help me out porting the head, help me out get the bowls cleaned up, get them deburred, the valve deshrouded, and that kind of stuff. So he did help me out with that. I also went and ordered a few more things. Now that I had the engine apart, I'm able to, now that I know the dimensions of the parts within the engine, I can go ahead and confidently order bearings, valves, the pistons themselves. So I went ahead and ordered that. A local company called Real Street Performance. They had all that stuff pretty much in stock, so they shipped it out. This was all during Hurricane Irma. So on top of all this, I was also delayed. Pretty much everything I had ordered was delayed due to the hurricane. We're fine here in Orlando, but it definitely did some damage, and a lot of the shipments and stuff slowed down to a crawl. So unfortunately, it's kind of just been a lull in activity on this engine. But I've got a lot of stuff in, and we should be finishing some stuff up this weekend, which actually involves porting the heads, cleaning the bowls, and I've got some videos showing that. A lot of it's just kind of monotonous work, just polishing things up and cleaning them up and trying to blend seams in, and just all that is just, you're just sitting there with a Dremel or with a grinder and just keep constantly just working inside those bowls. So it's not super exciting work, but I definitely have some video taken of it, so I'm gonna get that put up as well. So hopefully after this weekend is done, we'll have most all the head work done, and I'll be able to start getting all the stuff together to get this to the machine shop. And I'm really excited to do this. I am super ready to get this car back together. I also went ahead and ordered a fuel system from Flying Miata, the flex fuel kit, and I also ordered a cross flow radiator and some fans and a hose from them as well. That stuff's not even going to be in until November, so I'm kind of bummed about that. The fuel system should be in hopefully by the end of October here though, so by the time I'm putting the car back together, I hope to have that so I can install it at the same time. I'm gonna go ahead and try to keep on trucking here. I'm gonna pick up where I left off filming regarding measuring the journals and the bearing sizes and everything. Hopefully that's gonna kind of blend together well enough that we won't have any issues. The next video I put out there will be involving the head work, and because I'm going to try to divide that up separately. So we've got the measurements, why I ordered what I ordered, and then I'm going to start getting some videos together on the head work, polishing the crankshaft, and polishing the camshaft journals. These are just micro polishing. The journals measured fine, but we just need to get them polished up so they're even better. So these are almost like a mirror finish, like very fine. So just doing some of that work, and then hopefully I can get that stuff out to the machine shop and we can start rocking and rolling. Don't know how long it's going to take for him to do that work, but hopefully it won't be too long. I can understand when people are they'll slap together a build or get really anxious to finish it up, and it's really tempting. I can't tell you how jealous I am of anybody else with a Miata right now that's out driving around, because it's sitting in the driveway and I really, really want to drive it. But I know that it's going to be worth it in the end. I'm learning a lot doing all this stuff. This is really really interesting to me, and it's teaching me a lot, and that's the main reason I'm doing this, is to learn. I'm not just doing it because I want a car to do something. I could take it somewhere, pay someone, and have them build the car, but building it myself is really rewarding because I get to learn all about it. And so, yeah, it's tough, but in the end, I'm gonna enjoy the fruits of my labor. So, without further ado, I'll give you a quick tour of where I'm at. All right, so here we've got the crankshaft. This is already polished. You can see all of the all that odd gray stuff on there is actually sandpaper. So we went from a 600 to an 800 to 1000 or 1500, and the 1500 grit is that gray paper, which is why there's all that gray stuff down there. So these are all micro polished. I actually had an issue while I was shooting some of the video about the crankshaft. It was raining outside, and I mistakenly was saying to use oil on the crankshaft, and unfortunately that didn't work out because the oil floats on top of the water. So the water that hit the crankshaft got underneath it and created some small rust spots on the journals themselves. So we had to go through and sand those off with the high grit sandpaper. I did recheck these journals afterwards. They're all the same size. We took an immeasurable amount of material off. So I'm not worried about that at all. These are all within spec still, and everything's nice and polished up. It looks really good. So this guy is ready to go. And just for reference, afterwards I used WD-40. This is all soaked in WD-40, and that's keeping the water away from it. So that's water displacement formula 40. So it's displacing the water off of there, and it's just what I've been using as a protectant since I accidentally got a tiny bit of rust on here. Luckily I caught it in time before anything bad happened. It was only on there for a few minutes, but it still did a bit of damage. So down here you can see I've got all of my valves taken out, and I have a video on my valve removal tool, which is right here. I'll be posting that along with how to remove these valves. So you've got the intake and exhaust, and these are all labeled on the bottom here. So you can see these are the number 1, and these go from the front of the engine to the back. So these are all removed. We checked the play inside the valve sleeves, and they look just fine. So no worries there. Spin around here, and you can see some of the work we've been doing. May or may not focus very well, but this is kind of a preview of where we're at doing the bowl work. There are a couple of nicks in the surface of the head itself. I accidentally dropped the head an inch or two, and it fell onto something, and I think it marred a little bit of the near one of these bowls. So hopefully they can deck that out, and there won't be a big issue. It's fairly shallow, so I'm hoping that turns out to be fine. But you can see these are, I have some before and after pictures, and I'll add those, but these are all really smooth. So these have been kind of ground down and polished. The valves here have been blended in, and I'll have some more information on this in the video about how we're going about doing this. The porting is next. These guys still really dirty. There's not much porting work to be done, luckily, so everything inside is actually fairly well shaped, so no big reshaping. We're just gonna kind of polish things up and clean them up, and that's about it. But definitely did a lot of work on this, a lot of hours in this already. So I'm going to start off, since we've got the whole block torn down, I'm going to start off with a the kind of most obvious thing, which is the pistons. So to start out, there's a ton of different stuff out there as far as pistons. There's, you know, manufacturers, there's Wiseco, there's CP, there's SuperTech, there's a whole ton of other ones out there that are making pistons. There's different alloys, there's different rings, there's all kinds of different things that are kind of going to selecting a piston and selecting the right piston for your application. So I've been doing a ton of research on this to try to figure this stuff out, because I had no idea there was this much stuff out there. I had just seen one or two piston sets on some websites and thought that was it, but apparently there's quite a bit more to it. So start out, the pistons themselves. So the big thing that you gotta start with is bore size. So your piston is gonna fit in that bore, that the cylinder inside the engine. It's going to sit inside that bore, and it has to sit within a certain tolerance along with those rings. So usually those are two things you order at the same time, because the rings are sized to the bore along with the piston. There's a clearance between the piston and the wall of the cylinder. So when you buy the piston, you get a certain diameter piston. It might not be actually that diameter. So you'll say the stock Miata is an 83 millimeter bore, and you need to order a piston for that. You might not get an 83 millimeter piston, because if you did, the clearance would be so small that it wouldn't actually work. So the piston itself reads a little bit smaller, and I can demonstrate that right here. All right, so what I have here is the stock piston out of the Miata. So this is an 83 millimeter piston, and this is what comes stock in the 2002 Miata. They call this 83 millimeters, but the bore actually measures 83 millimeters almost exactly within probably a half thou or so. What we're gonna do is measure this with a micrometer and see what it reads. So let me wipe my hands off really quick. So what I'm going to do here is I'm going to take this micrometer, going to run this out, and just looking at this, we're already at 85 millimeters, just to kind of get this in along this piston. What I've done is I've brushed off the carbonization on this piston just so that it's going to be a clean spot to test this at. And I know you can't see too close, but I'll go over this in a little bit. So basically just measuring this piston. All right, so I've measured that, and according to the scale, this piston is 82.32 millimeters. So the piston, the bore itself is 83 millimeters, but this is reading 82.35 millimeters. So the piston's actually a fair bit smaller than the bore itself, and that's to account for the rings. So the rings, as you can see, there's actually 3 of them on that piston. 1, 2, 3. And with that, you've got the first ring, the second ring, and the oil control ring. So those are what actually help to seal the combustion gases inside the cylinder, so when you're burning you don't get a ton of blow-by, which is gases escaping into the crankcase, and you get all of the power out of that compression stroke, or that power cycle. So our stock bore is 83 millimeters. That means there's a couple things we can do with that. We can either use it at its stock size, rehone it, and make sure that we're within tolerance for the rings that we'll be getting for that stock size, or you can do the thing that most people do, which is to overbore the cylinder. Now, being that the Miata has a cast iron block, the BP engine is pretty easy to overbore. It's very strong, which means that you don't have to worry too much about boring those cylinders out if they're going to damage the cylinders and make them too thin to support higher power, which is usually what people are going for when they rebore an engine. So what we'll have to do to find out where we can go with this engine is to see what size the initial bore is. And that's going to be done with a bore gauge, which is a simple tool that's used to determine the size of the bore. We'll do that a bit later. For now, we're going to talk about the type of alloys. And there's 2 types of alloys that are really common. That is 2618 and 4032. Now these are both aluminum alloys. alloys, and one of them, 2618, is a softer alloy, so it's more ductile, meaning it can be flexed more. It's not as rigid. So it's the difference between something being very stiff, like some plastics are, when you bend a piece of plastic, it snaps immediately, and some other ones where you bend it, it's soft and it just bends. So that's the difference between brittle and ductile. Now, the harder metals tend to be stronger in that they wear harder, so they don't wear as badly over time. So you'll get more longevity out of them at lower power levels. However, the 2618 is stronger in that it holds up to detonation a little better. The sudden explosion that occurs when a detonation event happens is somewhat absorbed by the piston, and it doesn't actually shatter, it just bends a little bit. Now, too much detonation is going to ruin any piston. Detonation is never a good thing. So the fact of the matter is that these survive a little bit better in these type of builds, and they're commonly used for higher horsepower vehicles because they tend to have more of a likelihood of detonation, and they also put a lot of stress on their engines. If you were building this engine to be the longest life possible without getting back into it, without rebuilding the engine, you might want to look at a 4032 type of alloy, because that's going to give you a better wear life. So it's a similar fashion with bearings, but I'll get into that a little later. But those two type of alloys are the most common that you'll see when you're looking for pistons. So what I've decided to do is go with a 2618 piston, and that's because it's going to give me the most resistance from detonation. I don't mind getting back into the engine and rebuilding it later on. I might have to, and that's all part of the learning process. So what I'm going to do is get a set of pistons on the second overbore for my engine size. What that's going to be is the OEM size is 83 millimeters. The first overbore is 83.5 millimeters, also known as 20 over because it's 20 thousandths over the OEM size. The second overbore is going to be double that, so it's going to be 84 millimeters, so a full millimeter larger in diameter than the OEM bore. It's also called 40 over, it's 40 thousandths. And you'll hear that thrown around a lot if you're going to bore 20 over, 40 over, and that will actually increase the displacement of the engine at the same time. It's not a huge amount, but it will just increase that displacement. So you'll go from a 1.799 or a 1.82 liter to something slightly larger, a little bit closer to 1.9 liters. Now the second thing is rings. So rings are those pieces of metal that seal the combustion inside the cylinder, prevent it from escaping down into the crankcase. They also help hold the piston in line within the cylinder so it doesn't slap. Piston slap is what happens when the piston actually rocks inside the bore side to side, and that can be from a variety of reasons, including the clearance being too large between the piston to wall and the piston not having warmed up properly if it's one of the softer and more ductile alloys. Now there's a couple downsides to running the more ductile piston. It's not just a free lunch. The more ductile piston will be softer, so it will wear more. Just riding in the cylinder, it's going to wear more than a harder piston. And also, the more ductile piston, the materials that go into it, the increase of silicon in the metal causes it to expand more when it's heated. So the piston to wall clearance has to be greater in order to prevent that expansion from making the piston hit the wall as it heats up over time. So when you first start the car up, you're going to get a bit of a piston slap when the car is still cold. Now, as far as piston rings go, which are kind of the next thing on the list, these are a bit of something I still don't fully understand. And honestly, there's a lot that goes into piston rings. There is a ton of different shapes. There's a bunch of different compositions. There's coatings. There's all kinds of stuff. And generally, the rings are made specifically for a piston design. So there's certain slots that can be carved into the piston that will enable certain rings to be used, different depths of slots, and pretty much they're built to change the sealing properties of the piston. Some of them have special designs to make them seal better at the expense of increased wear, and that can be used in things like race engines where they are rebuilt frequently, but the wear isn't that big of a deal because they're constantly being replaced. There's other types that will wear less but seal lighter, which gives you the benefit of less wear, but at the expense of, ultimate horsepower. You won't be able to get as much horsepower, you'll get greater blow-by, and it can contaminate the oil more and require a better catch tank and some other things. So there's a ring for every use, really. There are a ton of them out there. What I've done is I've kind of taken the easy way out. The manufacturer that I've decided to go with for the pistons, JE, specifies a set of rings to go with the pistons, and I'm just going to trust them on that. So I'm going to go ahead and just purchase the pistons. Actually, the piston set that I'm getting comes with a set of pistons. It comes with a set of rings, so there's a set of 3 rings for each piston, as well as it comes with the wrist pins, which are the pins that attach the piston to the connecting rod, and they come with the clips. So there's a little clip inside of there that is used to hold in the wrist pin and keep it from falling out. So I'll stick with that for now. If it's a problem down the road, I'll have it tear down and I'll explain why. The next thing on the piston itself that we'll be looking at are the connecting rods. Now the connecting rod is, as it says, the rod that connects the piston to the crankshaft. So what we've got at the top is the wrist pin, and this allows the piston to move left and right as this moves through its motions inside the engine on the crankshaft. It allows the piston to rock back and forth on the pin. And then at the bottom here we've got a set of bearing journals. So these bearings ride on the crankshaft journal, and there's a small film of oil that's kept flowing inside of here by the crankshaft. There's a hole in the crankshaft that flows oil in, and that actually lubricates this and prevents these 2 metal pieces, this bearing and the crankshaft journal, from touching. So that's basically what keeps the whole engine running is this mechanism here. Now for my connecting rods, I'm going to be replacing these, and the reason why is that these stock rods, so these stock cast rods here are actually fairly weak. So they're probably one of the weakest things in the engine, from the factory that is. The crankshaft is billet. These pistons are fairly strong, but it's well known that these connecting rods are not very tough. So if you run the engine at high RPMs, if you put a lot of extra power into the engine it wasn't built for, these rods will generally be the first things to fail. So what I'm going to do is replace those rods with some tougher forged rods. So these are castings that have been forged in a machine to compress those molecules and to really toughen up the whole piece of metal. So this is a Carrillo H-beam rod, and as you can see, we don't have a piston on it yet, but the insides are honed. This is ready to receive the bearings, the bearings that I select to put into this engine. It comes with its own caps, and this is what encapsulates the bearing. So as this is attached to the crankshaft, this bottom end cranks into here, and they have their own fasteners as well. So this is an entirely performance designed unit. You can see on the side of here, it's actually got a different shape than the OEM connecting rod. This has an H shape, hence the H beam. It's very wide as compared to the OEM. It's a much wider design, and it's actually got the center carved out, so it's also a little bit lighter. And so in this instance, this is going to be rated for probably well over 800 horsepower, whereas the stock rod could only handle a few hundred before it gives up the ghost. So I've got a whole set of these, and I will be joining these with the bearings, with the new pistons, and assembling these into the engine. All right, the next thing, crankshaft. So this is somewhat similar to the camshafts in that we've got to make sure that all the journals are measured, but this is a little different because with the crankshaft, we also have to make sure that we size this appropriately for the bearings that will be put into this. So each of the connecting rods has a set of bearings and the 2 shells that come together, and the same thing for each of the mains, which is what actually hold the crankshaft into the block and allow it to spin freely. So what I have to do to purchase the right size bearings is I have to measure the diameter of the journal, which is the crankshaft bearing surface, and then I also have to measure the size of the bore that the bearing will be going into. And depending on those two sizes, I then have to order an appropriate bearing. Now, if the hole in the block for the crankshaft bearing or the hole in the connecting rod big end is too large, if it's larger than the stock size of the bearing, I need to order an oversized bearing. And what that is a bearing set that has a larger outside diameter and the same size, a normal size inner diameter. Now, if this journal here has been ground, so if there's a defect on this journal, if it's scratched, if a bearing spun on it or something, if that's happened, then I have to get an undersized bearing. And what that will do is give me the same outside diameter with a smaller inner diameter. So that will be able to make up the difference, and it will be bored to handle that correct size. So without getting too much further into talking about this stuff, the only big thing about the bearings is that there are a couple different types of bearings. There's the stock aluminum bearings, which they're a somewhat hard grade aluminum, much like the pistons, the ones I had previously described, the 4032 type. And there's also a different kind of bearing, a tri-metal bearing, which has a couple different types of metals in them, and it generally produces a better bearing for higher horsepower applications. And so what I'm going to be doing is going with the tri-metal bearings, just simply because my end goal is going to be fairly high horsepower compared to the original OEM spec. So I'm going to try to use the best thing I can there, which appears to be tri-metal. So for now, I'm going to move on to actually measuring these components, and I'll show you how to set up and measure the bore, the piston, the clearances between these, and the journals on the crankshaft, all this stuff. So let me get out some instruments, let me get set up, and I'll start showing you how to do it. Alright, so the crankshaft is laid out here, the front and the back. What we're going to be doing is measuring the journals. Now the journals are each of these shiny areas on here, and these areas are where the bearings ride. So the ones that are along the center here, so this guy, this one, this one, this one, and this one, these 5 are the main journals, and those are what the crankshaft itself rides on to keep it in the block. These outer ones here are these 4 are for the 4 pistons, so each one of those a connecting rod attaches to, and that's for the bearing in the big end of the connecting rod. So what we need to do is measure each of these journals to determine what size they are, so you can order the appropriate bearing for this application. Now, with me to measure this today, I've got my Miata. This is a 25 to 50 millimeter micrometer. Now, we're going to be operating on the kind of far end of this, and I wish I had something a little closer, but this is what I've got, and it's within this range, so we're going to use it. Now, this is actually quite an accurate micrometer. This one goes down to 0.001 millimeters, so that's very small. And as you can see, there's like a Verner scale on here, so that we can measure extremely accurately. So just to make sure that when we do this, these faces need to be perfectly clean. So I'll need to wipe those off. If any oils and stuff that's on there can actually affect the reading. Any dust particles will affect it. So we'll also need to make sure that the areas that we're measuring on the crankshaft are also just as clean. Alright, so here at the front of the crank, we're going to start by measuring the journal on this crankshaft. There's 2 wear surfaces where the bearing actually rides. There's a spot in the center where there's an empty groove around the bearing where the oil flows through the bearing. So we want to make sure that you measure the 2 ridges on the sides where the bearing actually rides. And there's a slight bit of wear that can kind of be seen on there. So I've got my micrometer set, so I'm going to go ahead and just make sure these are clean. Make sure that the faces of the micrometer are clean. Alright, and I'm going to bring this down here. Slowly snug this up, kind of feeling for that spot. Feels like it right about there. I'm going to lock that in place, slide that off. All right, so looking at the micrometer, we can see that each of these vertical marks along here are going to be a 1/2 millimeter each. And then you've got this guy over here which kind of reads that out. So we've got 45, 46, 47, 48, 49, 49.5, and then our 45 is what's lined up with the base line here. So we add 45 to that 50 and you come up with 95. So it's 49.95 is our reading here, and the spec states that it needs to be within 49.938 to 49.956 millimeters. So according to this, we're within that distance. So we are within 0.5, and it seems to be pretty accurate. It's not actually over that, so I'm going to say that one's good. So now I'm going to go ahead and label, write down which one is which one of these bearings and what its actual reading is. Before I do that, I'm going to do another quick measurement on the other side of this just to make sure that these guys are aligned, are the same. There's not too much wear on one side that wasn't on the other, so I'm just going to go ahead and just do the same thing over here. And it looks like that's the same reading for the inner side here as well. Just for kicks, I'm going to measure the center area. Clean that off, make sure there's nothing on it. I'm getting the same for the center as well. So there doesn't appear to be any appreciable wear on this bearing right here. So I'm going to label that down. The 49.95 millimeters, and I'll move on to the next one and do the same thing. Looks like we're at the same measurement as well. This is also showing 49.95. So I'll go ahead and label that. And basically I'm going to continue down the line, each one of these mains, and then I'll go back and I'll do the same thing to the connecting rod bearings. Alright, so I've got all of the journals checked. They're all within spec, luckily, no problems there. A couple of them are a little, they're for the most part, they're all pretty close to each other. There's one of them, this guy is a little further out, but it's by a couple, 0.003 millimeters, so it's not a huge deal. I went ahead since I was wiping my fingers all over these, I went ahead and re-oiled all the journals just to make sure that they don't corrode or anything like that from my finger oils. Not that they really should, but I just wanted to make doubly sure. So now this is all good to go. The next thing to do is to check the mains in the block. So I'll show you how to do that in just a minute. All right, so need to measure a few things. One of the things we got to measure is the bore. So to measure the bores, both for the bearings and the cylinder walls, we need a dial bore gauge. So the bore gauge is basically, you saw it in the last segment there. The bore gauge is a dial indicator that's attached to a long stem here, and down at the end there is a small plunger. This is not really screwed on. There's a small plunger, and as this plunger gets pushed on, it actuates the gauge. So this device does not directly measure. So this doesn't give you a readout right here and tell you exactly what it is. You have to set this, and then this gives you a reference to tell you if it's over or under the amount that you've set it to. So I'll give you a quick rundown on how this operates. So you've got two heads. These heads here unscrew. I'm working behind the camera, so you'll have to pardon me if I'm sounding a little odd. set this down here. So this is one of the heads, and it basically is what contains the mechanism that this pushes against. So as I push on this piece here, that little bit at the top here slides up and down. Now these wheels here, they don't actually spin, but they're to center the device in the board. So the tip uses one of these, and that screws into here. So this here unscrews. I'll set this nut down. So in the end here, this just receives one of these pieces, and then the other end self-centers inside that bore, and there's a small spring action here, and that makes sure that this touches the inside of the bore and that we're getting an accurate measurement. So to set this up, there's a few things involved. So first of all, you have to choose the right diameter. So if you look at these, we've got 1.4 to 2 inches, which is also printed. This is a 2 to 6, which is a little difficult to see. I don't know if it'll focus on it, but this is 2 to 6 inches. It's just kind of stamped into there. And these are obviously in the wrong slots, but this one says 1.4 to 2.4 on it. So we're not going to use this obviously because we're not measuring that small of a bore. We're measuring 83 millimeters. So I want to say it's close to about 3 inches. So I can do a quick calculation here. All right, so we do 83 divided by 25.4, and I'll give you 3.26 inches. So about 3¼ inches. So what we'll need to do, and these are actually labeled as well. So this one says range 1.4 to 2 inches, and this one says range 2 to 6 inches. So what we got to do is select the right one of these, and then attach that into the right end with this guy, and then attach that into this gauge, calibrate the gauge, and then use the gauge to check the bore size. So to start out, we've got a few things. So I'll set this aside. So we have to size this appropriately. So what we've got to do is insert the right one of these guys, and so we need 3.25 inches. So this is 3.2, but we need a little extra size because if we put this in here right now, it's not going to fit. It'll just kind of flop around, and we can test that. If I can make this fit, we can test that over there, and I'll show you what it looks like. All right, so here's our cylinder bore, and here's our checker. We can see it fits in there, but here's the problem. So it fits snugly, but we can see that the end right there is nowhere near touching the cylinder wall. It's still pretty far out. So that's going to be an issue. So we can try the next size up. So the next size up is 3.4 inches. All right, so let's go ahead and test that. All right, so we'll slide it down inside the bore here. Oh man, there's a problem. Now I cannot get this to go level in here, which is how we check the bore. This has to be perpendicular to the bore inside of here. And the problem is that that piece is hitting against the wall. So because of that, we won't be able to measure, so it's too big. So, all right, so 3.2 is too small, 3.4 too big. And luckily these are easy to take out and in, so I'll set that aside. Now the other thing it comes with is these little washers. So these washers are things you can add on to this to size between these sizes. So these jump between sizes, 3.2 to 3.4. But in order to make this fit, we have to shim it a little bit. So we have to shim it, maybe, we could start with the larger one, let's say 0.12. Now this won't fit onto there, so what you have to do is you take the insert here, the anvil, and this slides right onto here. Drops in, and you can see now it's spacing it out by that amount. And now I just need my nut. That goes onto there. And you can see it doesn't screw down as far, but it's still okay. So I'll go ahead and check this really quick. Okay, that's perfect. That's gonna fit right inside of there, and there's enough clearance for this to stick out and touch the wall. That's a quick and easy way to set this guy up. If we measured this out, we would say that it was 3.2 inches plus 0.12 inches would be a 3.32 inches, which I believe is they list that as the maximum bore size. I think that this is, yeah, because if they don't list you a minimum on here, they just give you the maximum. So you kind of have to play around with it a little bit to find something that'll fit. All right, so we've got the end appropriately sized. This has the right combination of anvil and the little washer in here stacked up to give us the right depth to measure the bore. So we're measuring the piston bore. And now we just need to install this on the gauge end. So there's a washer it comes with, a little spacer, slides down onto here. So I just did the thing you don't want to do, which was to tip this up and let the shaft fall out of the inside of it. I may have lost one of the little pieces inside, a little shim that they use to support the rod inside that shaft, but it should not be a problem. So I'm just going to go ahead and push this guy up inside of here. Okay. And then we screw this end onto here. Okay. And don't worry about orientation, this is all in, this can all change. So we have to loosen this gauge up and the gauge can rotate, so no big deal. We will be rotating this as we adjust this setup. So I'm gonna go ahead and close this box up and we should be good. All right, so this is normally set using a micrometer. So what I've got here is a micrometer stand, and this is mainly to make things a little easier, especially since I'm filming, but it's a good way to make things a little easier on you. So I've got my micrometer here, which this should fit, even though it's got this little plastic piece. Interesting to note that plastic piece is actually to prevent your hand from warming the micrometer too much. It's not going to fit. I need to pop that off really quick, so just give me 2 seconds and I will take that off. All right, so it ended up not fitting. I had to pop the little temperature protection cover off of the micrometer, but no big deal. All right, so what we need to do here, since this is a reference instrument, this is going to be calibrated based on a set size here. So what first thing you do is dial in the size we want to check on the micrometer, and we'll lock it into place. So looking at the side here, we want to go to 83 millimeters is the bore. So I'm going to run this out to 83 millimeters. 81, 82 and a half. Looking for this zero here to line up. Okay, 83. I'm going to set that lock. So now my micrometer is locked into place. Check the anvils here, make sure these are clean. Any kind of contaminants on there can affect the measurement. Not such a big deal since this isn't extraordinarily accurate, but it is fairly precision instrument. So make this a little easier to see when I rotate my micrometer sideways, because you kind of have to see more this end than this end. So what I'm going to do here is I'm going to insert this end into my micrometer. It's a little difficult. It's kind of a two-handed operation. You have to have one hand keeping this centered up in the micrometer correctly, because if any deflection side to side, you're going to get a change in the gauge reading. Let's see if I can't lift this gauge up without causing problems. At the same time, you also want to be careful of the micrometer since it's a precision instrument and you don't want to damage it. And you can see this can be a little challenging. And now what I'm going to do is I'm going to loosen this screw up here, and this screw lets you spin this dial face. So I told you this is a relative instrument. It's relative in the fact that you're measuring what you've previously set. So this can all be altered, and we're just going to look at offset basically. So if I can hold this on here for more than 5 seconds. Okay. I'm going to take, I know there's a little bit of glare here, but I'm going to take and spin this dial. So you can see that that goes up a little bit and then comes back down. And that the farthest reading is what we want to read. So I'm going to adjust some things here. And at that farthest point, I'm going to rotate the dial here and I'm going to test it. Make sure that this is adjusted to exactly the farthest point, because that's the furthest open that this can go. Otherwise, it shrinks down. The opening as you tilt the gauge in the micrometer, it shifts. So I just accidentally tweaked the piece a little bit here. I'm gonna go ahead and lock this down so I don't accidentally do that again. Should have done it to start with, but you know. All right, that's pretty accurate. So I'm gonna this time carefully lock this gauge down. All right, so we should have a good reading now, and we'll bring this now over to the engine and see what we see. All right, so to measure the gauge, or measure the bore, we're gonna kind of make sure that there's nothing inside of here, and this looks pretty clean. It's got a light coating of WD-40 on it, but that should not matter. We're not getting to, tenths of thousands here. I know that this gauge does say 005, but the accuracy of the entire system with centering accuracy and everything else is within about 1,000. So we really won't be able to resolve that. So what you essentially do is you put this down inside the bore and you slowly bring it upright and you find the spot on the indicator here where it is where it goes the highest. So basically you're trying to get this tilted almost perfectly vertical, and you have to watch the gauge here. So I'm going to slide this down inside. I'm going to measure kind of near the top. Now the camera loves to back focus, so I got my hand in front of this. But as I'm doing this, you're going to see, as I bring this back and forth, this indicator goes up and then goes back down. So I'm rotating this along with the cylinder, so in the same axis as the cylinder. I'm rocking it left to right, and what I'm trying to do here is that the tool will center itself kind of side to side in the cylinder, but what we need to do is we need to make sure that that anvil is completely perpendicular, so that we're measuring the cylinder and it's at the correct diameter. It's right at its centermost point, that this is completely level, perpendicular to the head essentially, or to the plate on the top here. So as I'm doing this, you can see that this gauge goes up and then back down. So we're looking for is the highest measurement basically. So I'm kind of measuring and I'm looking, I think right about there is our highest measurement. And I know this gauge reach, each tick is 1/2 thou. So according to this, we're about it looks like 1/2 thou, a quarter of a thousandth over. So 0.00025. That's quite a small amount, and can probably be chalked up to some of this error within this tool. But it is going to be slightly larger since it is worn a little bit. It looks like for the most part these bores are within spec. And one of the things you want to check is you want to check in two directions. So you want to check in the first direction, and then you want to rotate it 90 degrees and check in the other direction. That's looking to see if the cylinder is oblong, and that's to see if it looks like an egg, like if it's not perfectly round. So I can do that. I can do a quick check. We'll look this way. Seeing about a quarter of a thousandth, and this way about 1/2 thousandth. So there might be a slightly oblong, but we also don't have this deck plate torqued down or anything like that. So basically got to do this for every cylinder. So basically we have to check every cylinder like this. Each cylinder needs to be checked, both dimensions, just to make sure it's within spec. Now I've already gone ahead and done that, and they're all within spec. They're not oblonged in any real way. That would be a big consideration if you were planning on simply rebuilding it in a stock form. But since I'm going to be boring these out to 84 millimeters, I'm taking an entire millimeter out of this inner area, and then the block is going to be rehoned afterwards. So any kind of slate oblonging or any kind of if this was off by, like, say 1/1000, it wouldn't be that big of a deal, because I'm taking out so much more material out of this to overbore that, I'm taking 40 thousandths out of these. Each cylinder, is enlarging by 40 thousandths. So it's basically a moot point. I just was doing it for reference and just to see how badly this block was worn before I got into completely rebuilding the engine. All right, now one of the things I've done is I've gone to King's site. This is the company that makes the bearings that I've purchased, King Racing. And this bottom bearing here is what I've got for the mains. So, so looking over here, they give you the specs. So this is the crankshaft journal size. You can see the arrows in the crankshaft. The crankshaft journal size needs to be 49.939 to 49.957. So this is the ranges in which these bearings will work. And then the housing, so the housing that holds the bearings in the block itself, this is what the range is right here. So what I've got to do is set my bore gauge to one of these sizes or somewhere in the middle, and then measure the bores and see what size they actually are, and that'll make sure that these bearings will work in the housings that I have right now. So I haven't actually measured these yet, so it's a little premature, but measuring the crankshaft journals and seeing that those were not worn at all pretty much tells me that there's no issues with the bearings that were in there. None of them were spun, so that should be just fine. But for kicks, I'm going to measure a few of them just to validate that they are correct. All right, so I've got my bore gauge set back up. I'm using the same similar stack up as before, that same 12,000 or 120 thousandths washer, and I've got the 2-inch anvil in here, and that is should total up to about 2 inches, 125 thousandths or so, 120 thousandths, and what we're measuring should be about 2 inches and 125 thousandths. So this has been dialed into exactly 54 millimeters. So I've got my micrometer here is at the 54 millimeters. So I've dialed 54 millimeters to be 0 on this, as the range is between 53.998 and 54.018. So essentially what we're looking for here is the bore needs to be within 2.125 to 2.126 thousandths, essentially. So that since this can read within about a thousandths pretty easily, it shouldn't be too big of a deal. I do have this snugged up quite a bit, so I torque these down a little bit, not to actual torque, but I'm just doing a cursory glance here. All right, so I'm going to slide this in and make sure you guys can kind of see that, hopefully. So I'm going to slide this in with a little pressure on the end there. All right, first time I've measured this. I have not measured this before. So let's see. According to this, I'm trying to kind of see this. Let me rotate it. This is saying we are about 1/1000th under what I've set. And I have set 54 millimeters, so... All right, so doing a bit of math, which is kind of difficult just because of the fact that this is standard and the bearings are measured in metric. Just doing another check here in a couple different directions. I am indeed seeing that this is about 1/1000th smaller. So 1/1000 would equate to 0.0254 millimeters, because it's times 25.4. So doing a quick calculation, 54 millimeters, which is what I've set this to, minus 1/1000 or 0.0254 millimeters is going to give us 53.974 millimeters. And this is not super accurate, but it's ballpark. So 53.974 is the reading that we're getting inside this bore, and the bearings themselves are calling for a minimum housing size of 53.998, which means we've got 0.098 millimeters smaller than we should. And if we take that and divide by 25.4, we get it's about 3 thousandths undersize. Now that's a good thing. It's not an issue, since this can be bored and honed. So this is something that the machine shop can do. They can, because these are slightly undersized, we can take these. They can bore these out to fit the bearings that are going to go in there. Now 3 thousandths, not a big deal. They can easily take that out with boring and honing, and getting the align hone done on this is probably a good idea anyways, just because the block has had time. It's got 80,000 miles on it. It's had time to settle. It's been through many thermal cycles since it was made, and doing an align hone just a good idea. It will take and basically let us bore all of these bores here, take all these surfaces, and along with the caps, they put these on and torque them down. They'll run a large bore through the center of this and a hone as well, and that will align, make sure that all of these are bored straight, completely straight, so that if any of these have shifted or the block is torqued a little bit since it was made, that will eliminate any of that torsion, which may be causing uneven wear on the bearings. It may cause something to lock up. I noticed looking at a couple of the bearings themselves, you could see wear on one side and not as much wear on the other. Not a very large amount of it, but it was there, which can mean that the block is slightly torqued. No big deal. They can take care of that. And what that does indicate is that the bearings that I have, there's plenty of material on this block for them to take off for those bearings to fit properly. So that looks okay. I'll go ahead and check one or two other of these, but to me that looks fine. And I'll double check with the machine shop. Obviously, when I do that, I'll have a nice video on how to do all that. But yeah, so for the moment, this looks fine to go along with the bearings that I've purchased. Now, the other thing that uses bearings is going to be the connecting rods. So I've got brand new curler rods that I'm going to be putting into there. And the nice thing about this is you don't have to measure these. They come with the measurements. So if we look inside the lid here, we can see they've given us a whole bunch of information here. So we've got how big the bolts are, the weights of everything, and we can see here the bores. So you've got the piston end and the bearing end bores. So these are the thicknesses, but this right here is what's important for the bearings. There's 1.8903 inches is the bore. So because of that, we can look at the bearings. The bearing spec is calling for 47.996 to 48.016 millimeters. And since this converted to metric is going to be 48.013, we are within the housing spec. We're actually kind of like right there in the middle of it, not a little towards the larger side, but those bearings should fit just fine. All right, so I mentioned earlier that I ordered some more parts, so I'm going to show them to you really quick. We got bearings. So these are King race bearings. These are the XP series, the tri-metal bearings. Just show you what they look like. These are connecting rod bearings. They come in a nice little package here. They are numbered right on there, 1 through 8. So these are the bearings that are going to go inside the connecting rods. And likewise, I have a set here of the main bearings. And there's 5 apiece, so 5 mains. So these will go inside the main caps, and this is what will hold the crankshaft into the block, or this is what they'll ride on with these bearings. Up next, I've got the valves. So I have new intake and exhaust valves. I figured if I'm buying the exhaust valves, I might as well buy new intake valves. One of the reasons I bought new exhaust valves was because, being that I plan on going to a forced induction, a lot of recommendations are made to go with a better valve, a larger valve, a stronger valve. So the ones that are in there, the usual steel ones that come with it, the OEM ones may not stand up to high horsepower operation. A lot of people get along just fine without them, but I decided to go. I'm going all out anyways. This is not exactly a low budget build, so I might as well just go with some extra valves. So what I've got here are the exhaust valves, and I've got one of them open. These are SuperTech exhaust valves. They are 1 millimeter oversized. So this valve is 1 millimeter larger in diameter than the stock OEM valve on the exhaust side. And don't know if you can see that, kind of bring it up there. It's got a nice kind of ground look to the bottom of it. These are made from Inconel, so they are high temperature metals. Not exactly easy to machine, but they are much better at standing up to high temperature than your usual, standard stainless steels or other types of metal like that the OEM would use. So I went ahead and got a set of these. They weren't that bad. I think they were maybe $150 or something for all the valves together. So this right here, I don't believe I have one of these open. Brand new, it's the unboxing. All right, so this is the valve for the intake. You notice it, you may notice it looks larger because it is larger. But the other thing you might notice is that the valve itself is cut right here. It's kind of got like a little, it leads in and then comes back out. That is a high flow valve, so the stem is ground down a little right here to allow more space for the air to get into the intake of the engine. So that's kind of an interesting feature. The OEM valves do not have that, so it should flow a little bit better than the OEM valve as well. Now, something about both these valves is these valves come about 0.6 millimeters longer. So the stem itself, below this keeper notch, the stem itself is 0.6 millimeters longer. Now, I asked SuperTech, and I asked a couple other people, I asked the internet, and the company that I bought these from, the retailer, about this. Because that valve is 0.6 millimeters longer, it won't have the same clearance to the OEM cams if I use the standard springs and the valve seats in the head, and it wouldn't ever close correctly. And basically what everyone said is the machine shop will take care of it. They'll take the valves and they'll tip the valves, or they'll grind the valves. They'll do various names for it, but they'll essentially take off the end of the valve to gain the clearance needed to fit inside of that, to fit with the stock cams. So I may have to change out the shims, because I'm not sure if you remember, but when we took that head apart, the 2002, the NB Miata, the second NB, the NB2, uses the shim on bucket cam style. So it doesn't use hydraulic lifters, so it doesn't automatically adjust. The shims have to be changed out. So depending on how that works, I'm not really sure if I'm going to have to take this stuff all down to the machine shop and have them check the lash or check the clearances on the valves there, or if I'm just going to have to, they're just going to do it and I'm going to order new shims. I'll find out about that later, and I will let y'all know how it goes. So this is the big box, and this is my box of pistons. I ordered Genie Pistons, as I mentioned previously. They are they're going to be overboard 40 thousandths or 1 millimeter. So, to a good look at that. That is a pretty piece of aluminum. This is all milled on the inside. They have some markings there. Yeah, if you can see, the Genie Pistons, and it has a serial number on here. So these are, this comes as a kit. So you've got the pistons, there's 4 pistons here. We have these special spiral rings which are what hold the wrist pins in. They clip into these indentations in the piston. And it also comes with a set of rings, so I can show you those as well. And it also comes with a new wrist pins. So that is a ground wrist pin. I can focus. It's a ground wrist pin. Not much to see there, just a piece of metal there, but it's ground to the right diameter to fit into this piston, this particular piston. And then this is the ring set. So these are all the rings needed for the cylinders, for the pistons. Sorry. So these I'll have to install all these as well, and I have a tool to do that. So we shouldn't have too much problem there. Of course, stickers. So last but certainly not least, it doesn't seem very important, but when you install the rings on the piston, the rings actually sit in an expanded state. When the rings are inside the cylinder, they're actually compressed. So they compress to help seal. Because of that, they're pieces of metal. They're pretty tough to compress. You need a way to compress them to put them into the cylinder without damaging the cylinder. Those rings get torqued side to side, or if they bend the wrong way inside of the cylinder wall, they can score it, and that just ruins all your honing. It can cause a lot of damage. So they have to be compressed, and there's a couple ways you can do that. There's a tool that grips, that slides around it. It has it's like a band, and it has a spot where you install a ratchet, and you use the ratchet to clamp it closed, and then the band will slowly shrink, and you use that to install it. That's an inexpensive way. I decided to not go the inexpensive way. This is a nicer way to do it. This is actually bored with a taper. So at the top, it's going to be one dimension, and give me 1 second and I can prove it to you. So I got my junky set of calipers here. So if I check the top of this, looks like we're measuring about 3.5 inches, basically exactly. Now I flip it over, all right, and I do the same thing on the inside, 3.25 inches. So there's a 1/4 inch of shrink from one side to the other, and what that lets you do is there's a small lip, and that lip sits right against the cylinder, or right into the cylinder. And what that does is that when you go to install the piston, you simply slide this over top of it. You slide this onto the cylinder. You drop the piston in, and you just simply push down, and it will slide it past the top of the head and let the rings expand as soon as it drops into the cylinder. So kind of cool. It's an easy way to do it, and it's also pretty safe. So that's kind of what I was going for with it. I didn't want any kind of fiddly tools. I know there's cheaper ways to do it. There's a lot of ways to do it, but I just kind of wanted to go the safest route, and to me, that's worth it for the peace of mind to not have to have my block fixed if I do something stupid, because let's face it, I make dumb mistakes. I know this video hasn't been super exciting just because it's been a lot of measuring, a lot of slow stuff, and I also know that it's been forever since I put up a video. As I kind of explained at the beginning of this one, it's been a while since I uploaded because I sat on a bunch of footage. And then I have to say that I feel even worse because I sat on that footage because I was busy doing a bunch of other stuff, including work, including some personal things, and also a lot of the stuff I've been doing has not been exciting. It's just been some really tedious stuff with the head. Behind me, you can kind of see my setup there with the head on the table, and I've just been doing a lot of grinding. It's a lot of just slow, boring kind of things. So the biggest thing for me is that I haven't had a lot of content to put up, and unfortunately I've been sitting on this video, so I'm finally getting it uploaded, and thanks to all of you who are still watching this. If you are still watching this, I swear I'll have some some more interesting stuff soon. I just got to get through this head, and hopefully in the next couple weeks I'll have this thing going to the machine shop and have some more interesting content. But I will get something up shortly regarding what I've been doing with the head, with the block, getting all that stuff ground out and getting it cleaned up and kind of ready. I've been doing a little porting work, so that's going to be interesting to see. So I'll get something together for that, and hopefully in the next couple days I'll have that up. And I hope to see y'all soon. Thanks for watching.